Imagine a summer so brutal that stone streets shimmer, animals collapse in the shade, and metal burns to the touch. Now imagine surviving that heat without electricity, without fans, without air conditioning, and doing it comfortably enough to live, work, and sleep. This wasn't a thought experiment. For centuries, medieval people in dry, scorching climates built cooling systems that didn't fight heat with power. They used physics. And in dry heat, many of those systems still outperform modern air conditioning in the one way that matters most. They cool without breaking when everything else fails. Modern air conditioning works by brute force. It consumes massive energy to push heat out of sealed spaces. Medieval cooling worked the opposite way. It never tried to defeat heat. It redirected it, delayed it, bled it away slowly, and used the environment as an ally. That difference is why medieval cooling systems didn't collapse during heat waves, and why many still function today. The foundation of medieval cooling began with understanding dry heat itself. Dry heat behaves differently than humid heat. Sweat evaporates faster. Shade matters more than airflow. Temperature drops sharply at night. Medieval builders observed this over generations and designed structures that stored coolness rather than chasing cold air. One of the most powerful medieval cooling technologies was thermal mass. Thick stone, mud brick, and rammed earth walls absorbed heat slowly during the day and released it just as slowly at night. In dry climates where temperatures swing dramatically between day and night, this created a natural temperature buffer. While modern buildings heat up in hours, medieval buildings resisted heat penetration until late evening, often after the sun had already set. By the time heat reached the interior, night air arrived to pull it back out. This is why medieval homes in dry regions were often coolest at the hottest part of the day. The walls weren't insulating heat in, they were delaying it. Modern drywall and hollow walls do the opposite. They heat quickly and trap warmth, turning homes into ovens during prolonged heat waves. Ventilation in medieval cooling systems was vertical, not horizontal. Hot air rises. Medieval builders exploited this relentlessly. High ceilings, clear-story windows, roof vents, and towers created natural convection currents. As hot air rose and escaped through upper openings, cooler air was pulled in from lower shaded entrances. No fans, no motors, just pressure differentials. In many dry regions, buildings were designed around courtyards. These weren't decorative. Courtyards created shaded, wind-controlled microclimates. During the day, shaded courtyards stayed significantly cooler than surrounding streets. At night, accumulated cool air settled into the courtyard and surrounding rooms. Rooms opened inward, not outward, protecting interiors from direct sun exposure. Water played a role, but not in the way people assume. Medieval cooling did not rely on flooding spaces with moisture. Instead, it used controlled evaporation. Small fountains, channels, or wet stone surfaces cooled air as it passed over them. In dry climates, evaporation pulls heat aggressively from the surrounding air. A small amount of water could cool a large space without raising humidity to uncomfortable levels. Clay and earthen materials amplified this effect. Unglazed surfaces allowed micro-evaporation, continuously shedding heat. The same principle used in clay water jars to cool drinking water was applied to entire rooms. Modern sealed materials prevent this. Medieval materials breathed. Urban design mattered as much as individual buildings. Medieval streets in hot, dry cities were often narrow, shaded, and irregular. This wasn't poor planning, it was climate engineering. Narrow streets reduced sun exposure. Tall buildings cast long shadows. Irregular layouts disrupted hot wind gusts and created cooler pockets of still air. Modern wide roads and open concrete spaces amplify heat instead of diffusing it. Another overlooked system was night flushing. Medieval people understood that the desert cools dramatically after sunset. Buildings were opened strategically at night to release stored heat and pull in cool air. Thick walls cooled deeply overnight, resetting the structure for the next day. Modern air-conditioned buildings remain sealed at night, trapping residual heat and requiring constant energy input the next day. Even roofs were engineered for cooling. Flat or lightly sloped roofs with light-colored surfaces reflected sunlight. Some roofs were layered with air gaps or earth, slowing heat transfer. In certain regions, rooftop sleeping was common, not because it was primitive, but because it was the coolest place available. Clothing and behavior completed the system. Loose garments promoted airflow and sweat evaporation. Activities slowed during peak heat. Work shifted to mornings and evenings. Cooling wasn't a device, it was a lifestyle synchronized with climate. What makes these systems superior to air conditioning in dry heat is resilience. Air conditioning fails when power fails. Medieval cooling doesn't fail. It scales with heat. The hotter it gets, the stronger evaporation and convection become. No grid, no fuel, no maintenance contracts. Modern architecture abandoned these systems not because they stopped working, but because they didn't fit industrial priorities. Thick walls cost space. Courtyards reduce rentable area. Natural ventilation conflicts with sealed environments. Speed and profit replaced climate intelligence. Yet today, as dry heat intensifies and power grids strain, architects quietly rediscover medieval principles under new names: passive cooling, thermal mass, night ventilation, evaporative design. These are not innovations, they are recoveries. And here's the uncomfortable realization. In dry heat, air conditioning doesn't beat medieval cooling, it overrides it temporarily. Medieval systems beat air conditioning because they don't collapse, don't escalate energy demand, and don't turn cities into heat traps. This raises a question modern society avoids. If people once cooled entire cities using stone, air, water, shade, and time, why did we build systems that require constant power just to remain livable? At dawn, the building began the day already cool. Overnight, thick walls and floors had released a heat they absorbed the previous day into the night air. Windows, vents, and doors were opened deliberately during the coolest hours to flush warm air out and pull cool air deep into the structure. This wasn't random airing out, it was thermal resetting. By sunrise, the building's mass was charged with coolness, like a battery. As the sun rose and outdoor temperatures climbed, the building was sealed strategically. Not every opening was closed, only those exposed to direct sunlight. Shaded lower openings remained partially open, allowing cool air to enter slowly. Hot air inside, lighter and rising, drifted upward toward high vents and towers. This created a continuous, silent airflow loop driven entirely by physics. By midday, when outside heat was unbearable, the interior reached its most stable state. While streets baked, interiors stayed remarkably cool. This wasn't because heat was blocked completely, but because it was delayed. Heat takes time to move through mass. Thick earthen walls slowed heat transfers so effectively that peak outdoor heat wouldn't reach interior spaces until late evening, often after temperatures outside had already begun to fall. This delay is something modern air conditioning cannot replicate. AC cools air, not structure. When power stops, heat floods in immediately. Medieval cooling cooled the building itself. Even if airflow stopped, the structure resisted heat for hours. In dry climates, evaporation amplified everything. Small water features placed in shaded areas weren't meant to humidify the space, they were meant to cool air selectively. As dry air passed over damp stone or shallow channels, evaporation pulled heat out of the air. The air didn't become heavy or sticky, it became cooler and denser, sinking into living spaces. Crucially, medieval builders avoided overusing water. Too much moisture ruins comfort. They understood balance intuitively. Water was exposed to air briefly, not sprayed or misted endlessly. The goal wasn't cold, it was tolerable, sustainable relief. Materials mattered more than shape. Mud brick, adobe, limestone, and rammed earth all share one critical property: high thermal mass with low thermal conductivity. They absorb heat slowly and release it slowly. Modern concrete absorbs heat quickly and releases it into interiors. Drywall does almost nothing except trap hot air. Another forgotten detail is surface texture. Medieval walls were rough, uneven, and porous. These textures increased surface area, allowing heat to dissipate more effectively and moisture to evaporate microscopically. Smooth, sealed modern surfaces reflect heat inward and prevent evaporation entirely. Ceilings were higher not for luxury but for survival. Hot air collected above head level. Sleeping platforms were kept low. In some regions, people slept on floors during peak summer because that's where the coolest air settled. This wasn't discomfort, it was optimization. Urban scale amplified these effects. Entire neighborhoods were designed to cooperate thermally. Buildings shaded each other. Streets acted as wind channels. Courtyards aligned to prevailing breezes. Heat was shared, diffused, and redirected rather than trapped. Modern cities break all of these rules. Asphalt stores heat, glass traps it. Wide streets expose surfaces to sun all day. Air conditioning ejects heat outside, raising ambient temperatures and making neighboring buildings hotter, a feedback loop medieval cities never created. Perhaps the most important difference is failure behavior. When air conditioning fails, conditions worsen rapidly. When medieval cooling systems were overwhelmed, conditions degraded slowly. People adapted behaviorally. They moved spaces, they rested, they changed schedules. The system didn't collapse, it flexed. This flexibility is what makes medieval cooling superior in dry heat. It doesn't demand constant input. It responds naturally to extremes. It assumes power loss, resource limits, and long summers. Modern architects now chase these ideas under terms like passive cooling, thermal buffering, and low-energy design. But stripped of jargon, they are rediscovering medieval intelligence, the kind built by people who had no choice but to get it right. To push this even further, we have to confront something most modern discussions avoid. Medieval cooling worked not because people were smarter, but because their systems were honest about heat. They never pretended heat could be erased. They assumed it would arrive, stay, and punish mistakes. Everything was designed around managing that reality minute by minute. Let's trace what happened during the worst days of summer when dry heat pushed past comfort into danger. By late afternoon, outdoor temperatures in dry regions could become lethal. Medieval people did not try to live normally during these hours. This is where the cooling system extended beyond walls and vents into time itself. Daily life was restructured. Work stopped. Movement slowed. Interiors became sanctuaries, not activity spaces. Cooling was not just architectural, it was temporal. You didn't fight heat at its peak, you avoided it. Inside the building, heat that had finally penetrated the outer walls was already losing its power. As night approached, outside temperatures dropped rapidly, a defining trait of dry climates. Medieval structures were built to capitalize on this drop immediately. Upper vents were opened first, releasing trapped warm air. Lower openings followed, drawing in cool night air like a tide. In some regions, entire buildings were reset every night, flushing heat completely before dawn. This nightly reset is something air conditioning fundamentally cannot do on its own. AC cools air but leaves structure warm. Medieval cooling cooled structure. By morning, the building itself was cold again. Floors, walls, ceilings. That stored coolness became the defense for the next day. In desert edge regions, wind towers and high vents intensified this process. These structures didn't catch wind randomly. They were oriented deliberately toward prevailing night breezes. As cool air descended, it displaced warm air upward and outward. The taller the vent, the stronger the draw. This created pressure-driven airflow without noise, power, or maintenance. When wind failed, convection still worked. Redundancy was built in. Another layer often ignored is light management. Medieval interiors were dim by modern standards for a reason. Light is heat. Windows were small, deep-set, and shaded. Overhangs and recesses prevented direct sunlight from entering living spaces. This wasn't aesthetic darkness, it was thermal defense. Modern glass walls invite light and heat indiscriminately, then rely on machines to undo the damage. Even color mattered. Light-colored plasters reflected heat. Lime wash was reapplied regularly not just for cleanliness, but because it reflected solar radiation and resisted microbial growth. As lime aged, it continued to brighten surfaces, extending cooling effectiveness. This was maintenance as climate control. The ground itself became part of the system. Many medieval homes were partially sunken, using earth as insulation. Earth temperatures remained stable even during extreme heat. By lowering living spaces just a few feet, medieval builders accessed cooler ambient conditions without digging cellars. Floors stayed cool underfoot, air near the ground stayed denser and more comfortable. Sleeping arrangements reveal how deeply this knowledge went. Beds were moved seasonally. In extreme heat, people slept on mats, low platforms, or directly on floors where cool air pooled. In some regions, sleeping outdoors on rooftops wasn't desperation, it was optimization. Roofs radiated heat upward after sunset, becoming the coolest place available. None of this required technology, it required attention. What modern observers often misunderstand is that medieval cooling systems were not static designs frozen in stone, they were interactive systems. People opened and closed, shaded and exposed, wetted and dried based on daily conditions. Cooling wasn't automatic, it was participatory. That participation is what made the system resilient. Air conditioning removes participation. You set a temperature and forget the environment exists. Medieval cooling demanded awareness. People knew where the cool air was at different hours. They moved through buildings like sailors through currents. Architecture taught behavior, and behavior reinforced architecture. This is why these systems fail when copied superficially today. A thick wall alone doesn't cool a house. A courtyard alone doesn't cool a building. Medieval cooling worked because every element supported every other element, and because human behavior completed the circuit. And this brings us to a critical realization. Medieval cooling systems beat air conditioning in dry heat because they scale with scarcity. When water was limited, evaporation was minimized. When wind was absent, thermal mass took over. When nights were cooler, flushing dominated. No single resource was overused. Air conditioning scales the opposite way. The hotter it gets, the more energy it consumes. The more buildings use it, the hotter cities become. The system creates the problem it is trying to solve. Medieval cooling never created heat islands, it dissolved them. The deeper we go, the clearer it becomes that these systems weren't abandoned because they stopped working. They were abandoned because industrial society prioritized speed, density, and uniformity over climate intelligence. Thick walls slowed construction. Courtyards reduced rentable space. Adaptive behavior conflicted with fixed schedules. Yet as dry heat intensifies and power grids strain, these old systems quietly return, not as nostalgia, but as necessity. We can keep going by examining how one medieval house was designed room by room for cooling, or how entire medieval cities cooperated thermally, or why modern passive cooling often fails where medieval systems succeeded.